Okay, next we continue with the last step, which is calculation. So calculation are based on stoichiometry. So the mass relationship between the analyte and the sample actually win. So a balanced chemical equation will give the ratio in terms of mole of the substance consumed or produced in a reaction. So if the mass of any one species used or produced is known, then the others are readily calculated. For example, here we have sodium iodide react with lead nitrate, producing solid lead iodide and remaining aqueous sodium nitrate. So if this is readily known, then the product here is easily calculated. Now let us see one example here to determine chloride. Okay, we go back to the reaction between sodium chloride, aqueous, and also silver nitrate aqueous, producing solid silver chloride and also remaining sodium nitrate. Okay, make sure the reaction is balanced, chemical reaction is balanced. So we have one sodium here, one sodium here, one chloride here, one chloride here, one silver, nitrate. Okay, so the mass of sample of unknown chloride, okay, this chloride, okay, in this case it's a non-chloride, which is silver chloride. So after drying, the mass is 0.0984. Okay, the mass of silver chloride precipitate is 0.2290. Oh, okay, this one is mass of sample of unknown chloride after drying. Only chloride. Okay, only chloride. Okay, so mass of silver chloride precipitate is 0.2290 gram. 1 mole of silver chloride contain 1 mole of chloride ion. Okay, here. So if that dissociate become ion, you get silver plus and chloride minus. Okay, 1 mole each. So therefore, the mass of the precipitate divide with the molar mass of the silver chloride, which is 143.323 gram per mole, we get 1.598 times 10 power negative 3 mole of silver chloride. Okay, so in this mole of silver chloride, we have only 35.453 gram per mole of chloride ion. This is the atomic mass. Okay, so therefore it is from this mole here, only this mole here and all, and this mass here, only 0.0566 gram is represented by the chloride ion only. Okay, so the percentage of chloride in this silver chloride precipitate is 0.0566 divided with 0.0984, okay, mass of the unknown chloride after the drying process times 100. So therefore the percentage of chloride in the unknown sample is 57.57%. So this is the general formula that you have to memorize in order to find the percent of analyte, which is the weight of precipitate, okay, multiply with the gravimetric factor, divide with the weight of sample, multiply 100. Okay, so what is gravimetric factor? Okay, so gravimetric factor is a combination of the mole ratio and the formula weight used in the stoichiometric calculation. Okay, so basically gravimetric factor is substance salt over substance non. Okay, I'll explain this later. Now, what is substance salt and what is substance non? we look at this example here. Okay, so you were looking for sulfur trioxide, so this would be the substance salt. Okay, you were looking for, and your precipitate was barium sulfate. Okay, so this would be the substance non. Okay, so we substitute this into the formula of gravimetric factor GF. Okay, we get this. This is obtained from the formula weight of the sulfur trioxide, and this value here 233.39 is the formula weight obtained from barium sulfate. Okay, so we refer what is the barium atomic weight, sulfur atomic weight, oxygen times 4 atomic weight. So we get this. So we divide. We get 0.343. So this would be the gravimetric factor value. Okay, so there's only one sulfur here, okay, for substance salt, and there's only also one sulfur here for substance non, so there wouldn't be any issue, okay, because the mole ratio is 1. But if the substance salt is different from the substance non, we have to take into account the stoichiometric. Okay, for example, let's say we have S2. Okay, let's say this is not SO3 but S2, for example, S2, and then the substance non is barium sulfate. Okay, so now the stoichiometric value is not balanced because we have 2 sulfur here and 1 sulfur here. We only focus on the analyte of interest. In this case is sulfur. Okay, so you can ignore oxygen, barium, and although it's not balanced. For example, here 3, here 4. Okay, we only focus on the analyte of interest. So let's say this one just now. Okay, 2 here for substance salt, 1 here for substance non. So it's not balanced, stoichiometrically not balanced. So what we do is make it balance. So how to make it balance? So the bottom part, denominator, times 2. So because times 2, sulfur becomes 2. Okay, so therefore this 233.39 times 2. Okay, then we divide. That's how we do. That's how we do it when we want to find gravimetric factor value. Here is an example when the stoichiometric value is not 1 to 1. For example, substance salt is silver oxide. Substance non is silver chloride. So you see here, 2 silver here on the nominator, and then only 1 silver here in the denominator. So not here times 2. Okay, so the formula weight here for denominator times 2. So we get the gravimetric factor 0.808. Again, we ignore other constituent like chloride here or oxygen here. Focus on the one similar, which is the analyte of interest. Now let us look at example 1 here. Okay, so this is the weight of a sample, okay, ionic compound containing chloride ion, and an unknown metal is dissolved in water treated with excess silver nitrate. So if 1.0882 gram of silver chloride precipitate forms, what is the percent by mass of chloride in the original compound? Now how do we solve this question? Okay, you have to use the formula that you should memorize in the earlier slides. So this is how we solve it. Okay, this solution is breaking everything in smaller parts. The best way to solve that question is to use the formula, the general formula in the earlier slide, which is percent of analyte of interest. Okay, analyte of interest. Okay, equal mass of substance salt. Okay, substance salt over mass of substance non times gravimetric factor times 100. Okay, So what is the mass of substance salt just now? Okay, the mass of substance salt, if we refer to the earlier slide, is mass of substance salt is 1.0882. Okay, mass of substance non, which is the mass of precipitate. Let me just put it as precipitate easier. Okay, mass of precipitate is 0.5662. So times gravimetric factor, in this case is the percent of chlorine just now, right? So here chlorine over silver chloride precipitate. So 1 to 1 stoichiometric ratio. So therefore 35.45 over 143.4 gram. And then we times by 100. So we should get the final answer, which is 47.51%. Okay. Okay, next example. Okay, 0.3222 gram sample of ionic compound containing bromide ion is dissolved in water and treated with excess silver nitrate. If the mass of silver bromide precipitate forms is 0.6964, what is the percent by mass of bromine in the original compound? Again, we solve this using the general formula that you should memorize. Okay, so we want percent of bromine. So substance salt is bromine. Okay, substance non is silver bromide. Okay, that times gravimetric factor times 100. Okay, so here the mass of bromine obtained is 0.6964. The mass of precipitate, so let's say we put this as the gravimetric factor of bromine and silver bromide. So here instead we put mass of analyte over with mass of precipitate. Okay, so here is 0.322 times gravimetric factor, which is bromide and silver bromide. So the ratio is 1 to 1, shouldn't be a problem. So 79.9 over 187.8 times 100. So we should get 92.02%. Okay. Next, we move on to precipitation equilibria. So when substance has limited solubility, means we can say it's an insoluble compound, the ion of the dissolved portion will exist in equilibrium with the solid material. Okay, so therefore the overall equilibrium constant is known as the solubility product KSP for the substance with that limited solubility in equilibrium. So consider this, okay, silver chloride in aqueous form. So when it dissociate, it will form silver plus and chloride minus ions. So when we write the solubility product constant, okay, this is the initial that solid that we obtain from the reaction between NaCl and Ag and O3. Okay, so we get NaGCl and also NaNO3. So this is actually just now in solid form. So when we put this in water, okay, we try to dissolve the solid. Okay, this is what we get. Okay, silver chloride aqueous, silver and chloride. Note that we have the arrow pointing at both direction because it exists as equilibrium. This actually represent equilibrium. Okay, so only a small portion of this silver chloride dissolve in aqueous form. So that's why we represent it as KSP, solubility product constant. Okay, so it is actually represented by the silver and chloride respectively. Okay, so let us look at this example here. Okay, so solubility product constant KSP of silver chloride at 25 degrees Celsius is 1 times 10 power negative 10. So this value here, okay, normally you can find it in the appendix section in any textbook. Okay, so calculate the concentration of silver and chloride in a saturated solution of silver chloride and the molar solubility of silver chloride. So there are two questions being asked here. Okay, finding the concentration of each silver and chloride, finding the molar solubility of the silver chloride. Now, the first step is to write the dissociation equation for silver chloride salt when it dissociate into ions. So we have silver chloride dissociate into silver and chloride. So when we write the expression for KSP, we get KSP equivalent to square bracket of silver and chloride. So the square bracket represent the concentration. So let us abbreviate. Okay, abbreviate using letter S. Okay, since each mole of silver chloride here dissolve to give 1 mole of silver and also 1 mole of chloride, so we can use S to represent this. Okay, so given the KSP value just now is 1 times 10 power of negative 10, and we abbreviate this, so we get S squared. So we can solve for S. In this case, S is 1 times 10 power negative 5 molar. So therefore, the concentration of each silver and chloride is 1 times 10 power negative 5 molar. Okay, so we have solved the first part of the question, which is the concentration of each silver and chloride ions. Next, what is the molar solubility? So molar solubility of silver chloride is represented by individual of this ion, which is 1 times 10 power negative 5 molar. So we have solved the second question. Now there's a rule of thumb here. When the product is less than KSP, so in this case this one, okay, is less than the KSP, no precipitate form and we will have clear solution. When the product is equal to KSP, we will have a saturated solution. When the product exceeds the KSP, a precipitate will form. So how about silver chloride here? In which category does it fall? Compare this 1 times 10 power negative 5 to the KSP value, which 1 times 10 negative 10. Which one is larger? The product. Okay, the product is larger. So when product is larger, it falls under category of a precipitate will form. Moving on to the next example. Okay, what is the solubility of lead iodide if the solubility product is 7.1 times 10 power negative 9? Now the first step we need to do is to write the dissociation of this salt, lead iodide. Okay, so this is already in aqueous form. Okay, after dissolving this, so this is the solid initially. So we get lead 2 plus and iodide. Okay, note that we put 2 here stoichiometrically. Reactant side, product side has to be balanced. So we have 2 iodide here because of this 2 here. Okay, now write the expression of KSP. So KSP is lead 2 plus iodide 2. So the stoichiometric value here 2 will become the power of the concentration here. Okay, so KSP is equivalent to lead times iodide power of 2 squared, okay, equivalent to the solubility product value KSP. So this is the KSP. Okay, so now we abbreviate like we did for the previous example. Okay, so let's say we abbreviate this and this. Okay, okay, we use the letter S also to abbreviate, okay, to represent, okay, the molar solubility. So then we can write this here, expression here as S. This one I is represented by 2I here, so 2S. So S and 2S, and we have squared here, so put 2 here. So 2 squared is 4, S squared. Another S, then it becomes 4S cubed. So how to solve S? We cube root the solubility product constant and then divide with 4. Okay, so we get S, which is 1.2 times 10 power negative 3 molar. Okay, so therefore the molar solubility is 1.2 times 10 power negative 3 molar. Now how are we going to solve this exercise? Okay, so we are given the solubility of lead iodide as 1.2 times 10 power negative 3 molar. What is the solubility in gram per liter? So the final answer is in gram per liter, and you are given in terms of molarity, which is mole per liter. Okay, so how are you going to solve this question? You are given the formula weight of lead iodide, which is 461 gram per mole. So we need the final answer in gram per liter, which is gram per liter. So we multiply so that we can cross these two. Okay, so 1.2 times 10 negative 3 molar times 461, and we get the value in gram per liter, which is 0.55 gram per liter. Next, we move on to common ion effect. Now, what is common ion effect? Common ion effect is where there is a presence of a common ion, and this presence of this common ion will suppress, okay, the solubility of the other ion, which is in common. Okay, so therefore the solubility become reduced, or solubility is decreased. For example, you have a solution which already contain sodium fluoride compound. Okay, so when this dissociate, you get sodium and also fluoride ion, but you are trying to dissolve magnesium fluoride in this solution containing sodium fluoride already. So therefore, less of this would dissolve because it already have sodium fluoride. The similar ion in this case which is fluoride. Okay. Another example, if an excess of sodium sulfate is added to barium chloride solution, this is the reaction which occur. Okay, barium chloride react with sodium sulfate, we get barium sulfate and also sodium chloride. Now this barium sulfate here is poorly dissociate, okay, and sodium sulfate here is strongly dissociate. Okay, so when we write the dissociation of each of these solution, this is what we get. Okay, barium sulfate produces barium and sulfate, sodium sulfate produces sodium and sulfate. This is strongly dissociate, while barium sulfate is poorly dissociate. Okay, so due to the common ion, okay, in the pore dissociation of barium sulfate, so this solubility is further reduced. So due to the presence of similar ion, common ion, which is sulfate. Now, how can we see common ion effect in more clearer view? Okay, we do problem solving involving value. Then you can see the difference. Okay, let us see one example here. Okay, 10 ml of 0.2 molar silver nitrate is added to 10 ml of 0.1 molar sodium chloride. So calculate the concentration of chloride remaining in solution at equilibrium and the solubility of the silver chloride. Okay, so we have two questions to be solved here. Concentration of the chloride remaining and the solubility of silver chloride. Okay, so we have 10 ml. Let me just write here. Okay, all the information given. Okay, that's how you solve problem. Okay, silver nitrate added to 10 ml 0.1 molar sodium chloride. Okay, so the final volume, because 10 ml is added to 10 ml, is 20 ml. That's the final volume. Now we have volume, we have molarity of each. So what we can get from here, what information? Number of mole. Okay, so we can obtain number of mole here. Okay, so m times v. Okay, so m times v, we get 2 millimole. Okay, because it's not converted to liter, so we get millimole. If you want to convert that 10 mil into liter, also okay. Okay, so your answer here, instead of millimole, become mole. Okay, so here millimole. Okay, so millimole silver nitrate plus sodium chloride, we get what? Silver chloride. Okay, the product is silver chloride. Okay, so silver chloride form 1 millimole. Okay, because 1 mole each. 1 mole here, 1 mole here, 1 mole here. Okay, stoichiometrically. Okay, has to be balanced. Okay, but this one is in excess, which is 2 mole. Okay, 2 millimole, sorry, 2 millimole. This is 1 millimole. Okay, stoichiometrically should have 1 millimole present, produced. So therefore this one is in excess. Okay, so 2 minus 1, 1 millimole silver in excess. Okay, so the concentration of silver, okay, is, okay, we are calculating the excess concentration here. Okay, excess concentration means, go back to the formula N mv. So we have volume, we have N, we can solve M. Okay, V in this case is 20 mil because it already been added. Okay, added. N is the different here, 2 minus 1, so 1 mole. Okay, excess. So 1 millimole divided with 20 millimole, 20 mil, we have 0.05 molar, mole per liter. Okay, you can convert this into mole, you can convert this into liter, you still obtain the same concentration. Now go back to the KSP expression for silver chloride here, solid. Okay, so the KSP expression for the silver chloride is silver and also chloride. Given the KSP value, okay, from the appendix is 1 times 10 negative 10, and we have find the excess concentration of silver, which is 0.05. So we can solve chloride concentration, okay, which is 2 times 10 power negative 9 molar. So we have solved chloride remaining. Okay, next, the molar solubility of silver chloride. So molar solubility is represented by the solubility of the by the concentration of the chlorine itself. Okay, the one limiting, not excess. Okay, limited in quantity, limiting factor. So in this case, solubility, the molar solubility is 2 times 10 power negative 9 molar. Okay, the last part is volatilization gravimetry. Okay, so this is the composition of solid sample thermally or chemically. So volatile products of decomposition reaction may be trapped and weighed. Okay, in this case it's a direct analysis, or the residue remain after the complete decomposition may be weighed, which is indirect analysis. Okay, what does it mean by this statement here is that, let's say you want to determine the moisture content of a food. Okay, moisture content, moisture. Okay, moisture content. How are we going to do this? Okay, of course, you will weigh the initial mass of the food and the final mass of the food after drying. Correct? Okay, O is initial, F is final. Okay, so moisture content is final minus initial, right? So that will indicate the moisture content of the food. Okay, after it uh, achieve constant weight after drying. So that process to measure the moisture content is indirect. Okay, because indirectly you measure the food mass after drying and before drying, not the moisture content itself. So that is considered indirect analysis. Direct analysis means you are trapping the moisture. For example, during drying, you trap. Okay, you have a trap. Let's say you have a adsorption trap. So that trap is weigh first before absorption process, and then it is weigh again after it absorbed the moisture in the food. Okay, so that indicate direct analysis because it measure the mass of the moisture content. Okay, so that's the difference between direct analysis and indirect analysis. So the example of application of volatilization gravimetry is thermogravimetry. This is apparatus to determine sodium hydrogen carbonate content of antacid tablets by gravimetric volatilization procedure. Okay, so this is where the reaction mixture contained the bicarbonate and sulfuric acid is. So this reaction will produce water vapor and carbon dioxide. Okay, and at the same time nitrogen is flow inside the reaction chamber here. Okay, so these are the product produced, water vapor and carbon dioxide. So these products will go through a drying tube. So this is a drying tube containing calcium sulfate, okay, or diatrite, and these will absorb water vapor, okay, because it's a drying tube. So it will let carbon dioxide through, okay, carbon dioxide through, and it proceed into another tube, okay, and this tube contain sodium hydroxide or non-fibrous silicate, which is called ascaride, okay, and also calcium sulfate. Okay, so the reaction between carbon dioxide and sodium hydroxide will produce sodium carbonate and water. So that is example of setup of gravimetric volatilization procedure. Okay, so it measures in terms of volatile species. Okay, for example here, carbon dioxide. Okay, sorry, here, carbon dioxide. Okay, volatile species. So volatilization gravimetry will requires product of decomposition reaction to be known. Okay, so if it involves organic compound, it can be accomplished by combustion, and normally combustion will, of organic compound will produce volatile gases such as carbon dioxide, water vapor H2O, and also nitrogen gas. For inorganic compound, the products may depend on the decomposition temperature used. For example, the thermal decomposition of calcium oxalate monohydrate. Okay, so at temperature 100 to 250 degrees Celsius, there will be loss of water vapor H2O, and the residue will become calcium oxalate. At higher temperature of 100 to 500, there will be loss of carbon monoxide gas, and the residue of the inorganic compound will become calcium carbonate. And at even higher temperature of 700 to 850 degrees Celsius, there will be loss of carbon dioxide gas, leaving behind inorganic compound residue of calcium oxide. Okay, so this is an example of inorganic compound. Okay, so the product depend on the decomposition temperature. Lower temperature, the volatile species is water vapor. At moderately high, the product is carbon monoxide. Higher temperature, the volatile species is carbon dioxide. So what is the equipment used for volatilization gravimetry? It can be simple or it can be complex. For simple experimental design, it will normally use burner or muffled furnace, and the volatile products will be vented to the atmosphere, and the solid residue remain behind will be weighed using analytical balance. For complex design setup, okay, this will involve constant temperature decomposition or combustion, followed by trapping and weighing of the volatile gases, which is conducted in a closed container, and the volatile gases will be carried by a purged gas stream through one or more selective adsorption trap. So the application for quantitative volatilization gravimetry, example of direct analysis for inorganic analysis, determining inorganic ash content of organic material such as polymer and paper. Okay, so therefore the sample of the polymer and paper is weighed in crucible. Okay, and then the organic material is removed by combustion. So the organic content of the polymer and paper will be removed, okay, by combustion. So we burn these two sample here. Okay, so the organic material will be removed through volatile species. For example, just now H2O, nitrogen. Okay, so what remain behind is the inorganic ash. Okay, so that residue is heated to a constant weight using either burner or oven. For indirect analysis, for inorganic analysis, okay, so this type of application will be based on the weight of the residue remain behind after the volatilization process. For example, to determine moisture in a variety of products, like I have mentioned earlier on. Okay, so let's say we want to determine moisture content in food sample. So the pre-weighed sample, okay, will be the sample would be weighed first, okay, before drying, and then after drying, the sample will be weighed again. Okay, so the drying will be conducted with an infrared lamp or low temperature oven. Okay, so the weight remain behind. Okay, that indicates the moisture content. So that is indirect analysis. So next we move on to organic analysis, okay, or elemental analysis. So organic analysis normally would determine carbon, hydrogen, okay, in the organic material. So the sample will be burned in a stream of oxygen. So therefore, it will produce volatile species of carbon dioxide gas and also water vapor H2O. So these combustion products will be passed through a pre-weighed tubes containing appropriate adsorbent, and the increase in the mass of the tube will indicate the mass of the individual volatile species. Okay, for example, okay, the burning is conducted here. Okay, let's say the burning is conducted here. So this is our sample. Okay, so we burn the sample. So this sample will produce the volatile species. Okay, so it will be vented through, let's say, a tube here. Okay, tube here. So in this tube, there will be adsorbent trap. Let's say this is specifically for carbon dioxide. This is specifically for water vapor. And this adsorbent has been weighed first. Okay, timbang dulu sebelum letak dalam ni. Okay, then after burning here, the sample is let to go through this, vented through this tube here. So it will be absorbed by the selective tube here. Adsorbent, sorry, selective adsorbent. Okay, after the adsorbent had absorbed the volatile species, then we weigh this adsorbent trap again. So therefore, the difference in terms of the mass of this trap before the adsorption and after the absorption will indicate the mass of the individual volatile species carbon dioxide and also water vapor. Now let us look at quantitative calculation involving volatilization gravimetry. So we have 101.3 milligram of sample, and these are organic compound burned in pure oxygen, and then the absorbent tube used to trap the carbon dioxide increased in mass by 167.6 milligram. So determine the weight over weight percent of carbon in the sample. Now how are we going to answer this question? So the question wants us to solve weight over weight percent of carbon, and that is represented by the carbon dioxide produced from the reaction. Okay, so the mole of carbon will be equivalent to the mole of the produced carbon dioxide. Okay, so we can write this relationship here. Okay, moles of carbon equivalent to moles of carbon dioxide. Now how to obtain moles? Remember the formula that I want you to memorize. Number of mole is equivalent to mass over molar mass. So we write mass over molar mass for carbon and mass over formula weight of carbon dioxide. Okay, so what are the information given in the question is the adsorbent tube mass here. Okay, so increase in mass by 167.6. So this will indicate the mass of carbon dioxide. Okay, so this is 167.6 milligram. So what do we need to do first? Because normally formula weight is represented as gram per mole. Okay, so the unit won't be the same. So we have to change this into gram first. Okay, so that we get similar units. Okay, so divide with 1000 because milligram. Okay, 1000 gram equivalent to 1000 milligram equivalent to 1 gram. Okay, so the formula weight of carbon dioxide. Okay, this one is 16, this one is 12 gram per mole. So 16 times 2 plus 12, we get 44. So here 44 gram per mole. Now move on to carbon. We don't know that. Okay, we don't know this. Okay, the atomic weight of carbon is 12 gram per mole. Okay, so using this we can solve for this. Okay, in which the answer is 45.74 milligram, okay, or 4.57 times 10 power negative 2 gram. Now, we haven't solved the question yet. The question is asking for percent weight over rate of carbon. So how are we going to solve this? Okay, so we have obtained this, right here. Where do we get this? Okay, we get this from the mass of the sample. Okay, and then we times by 100 to get the percent, which is 45.15%. Okay, so this is exercise that you can try on. Okay, again, burning of organic compound in oxygen, okay, producing H2O, okay, and the adsorbent trap increase in mass by 13.7 milligram. Okay, so determine percent of weight over weight hydrogen in the sample. So similarly, what we did in the previous example, the hydrogen, okay, is represented by the water vapor produced, H2O. Okay, so we use number of mole. Okay, not here, stoichiometrically it's not balanced. There's 2 here, there's 1 here. So what do we need to do? We have to ensure that the stoichiometrically it is balanced. So what do we do? This is what we do. Okay, so this is what we do. Okay, 2 moles of hydrogen equivalent to 1 mole of H2O. So this side here, okay, is 2 moles. Okay, so that it's stoichiometrically balanced. So mass of hydrogen divide with atomic weight, mass of water vapor produced, divide with formula weight. Okay, so this information is given. This one we can obtain from predictable. This one can be obtained from predictable, so we can solve hydrogen. Remember the 2 over here. Okay, so make sure you times by 2 later on. Okay, here. Okay, times by 2. So the mass of hydrogen is 1.53 milligram, and the mass of the sample is 101.3. So times by 100, we can solve for weight over weight percent of hydrogen in the sample, which is 1.51%. This is another exercise that you can try. A sample of slag from a blast furnace is analyzed for silicon dioxide by decomposing a 0.5003 sample with hydrochloric acid, leaving a residue with mass of 0.1414 gram. After treating with hydrofluoric acid and sulfuric acid and evaporating with volatile silicon tetrafluoride, a residue with a mass of 0.0183 gram remains. So determine the weight over weight percent of silicon dioxide in the sample. Okay, so the question is asking for weight over weight percent of silicon dioxide in the sample. Okay, how are we going to solve this? Okay, so this is how we're going to solve it. Okay, first of all, we have to find mass of silicon dioxide. Okay, so read the first sentence again. Okay, it's analyzed by decomposing. So this sample first undergo decomposing. Okay, and a residue is obtained. This is the residue. Okay, and this residue then, after decomposition, undergo the treatment, okay, which produce this, okay, remain. Okay, so using this and this mass, we can obtain mass of silicon dioxide. Why we don't use this? Because this is the original sample. The samples undergo decomposing first. Okay, and we use this in the second step to determine weight over weight percent of silicon, which is the original mass here. Okay, so the difference here, divide with the original mass times 100, then we can solve for weight over weight percent of silicon dioxide. Okay, the last part of gravimetry is particulate gravimetry. So this is where the analyte is present in a form that may be readily separated from its solid, liquid or gas matrix. So depending whether it's solid, separated from solid form or liquid form or gas matrix, will be based on its approach. Okay, so there are two approach, which is filtration. Second one is extraction. So normally if it's in liquid form, then we use extraction process. If it can be separated from solid form, then we use filtration. Gas matrix, we can also use filtration because normally gas will have different particulate size. Okay, let us look at filtration approach first. Okay, so liquid sample are filtered through appropriate filtering medium, either by gravity or suction. What does it mean here is you use filter paper that you have folded into cone size, so you let it filter by gravity action, or you can use pump, okay, to fasten the filtration process. Okay, so it will suck, okay, using a pump. Okay, so the choice of filtering medium will depend on the size of the particulate and also the sample matrix. If the size is small, then you have to choose the smaller size of filtering medium. If the size is big, then big size is good enough. Okay, so for cellulose fiber filter paper, the size is based on its pore size. Okay, in range from 30 micrometer to 2 to 3 micrometer. For glass fiber filter, the pore size is smaller, okay, in the range of 2.4 micrometer to 0.3 micrometer. Okay, for membrane filter, the pore size range is also small, in the range of 5 micrometer to 0.1 micrometer. This is example of filtration of gas sample. Okay, in this case solid aerosol. Okay, so these solid aerosol particulate can be filtered using either single or multiple stage system. So what does it mean by single stage system? So in single stage system, the gas sample is passed through a single filter, means only one size or pore size of filter, and it retain particles which are larger than the filter's pore size. Okay, kalau pore size tu besar, maknanya gas partikel yang kecil-kecil can pass through. Okay, kalau kita pakai pore size yang kecil, then it can retain large particle to small particle also. Okay, so itu maksud single stage. What does it mean by multiple stage system? Means there's a series of filtering units used to separate the particles by size. For example, this is your tube. Okay, so you put different filtering medium here. Okay, for example, so this one is big size. Okay, big pore size. This one is medium pore size. this is small pore size. So when the gas sample is passed through this tube, okay, the medium and small can still pass through this big, but the big particulate will be retained here. Okay, next, the small size particle can pass through the medium pore size, okay, and the medium size will be retained here. Okay, and then continuing the last filtering unit, the small size of gas particle will be trapped here, okay, filtered here. So that's what it mean by multiple stage system. Single stage, you only use one size, okay. Smaller than this can pass through, okay. Okay, next we move on to quantitative application for particulate gravimetry. So particulate gravimetry, very common in environmental analysis involving water, air, and soil samples. Okay, for example, analysis of suspended solids in water sample. I'm sure you have gone through to this experiment in your practical class. So this analysis will filter appropriate volume of a well-mixed sample through a glass fiber filter, and then the filter is dry to a constant weight 803 to 105 degrees Celsius to obtain the suspended solid in the sample. Okay, means if you have this liquid water sample, there's a very fine particle of suspended solid. We can separate this from its bulk, okay, from the water sample itself, by using this glass fiber filter. And then to obtain the mass of this, you have to get rid of the remaining water. That's why you have to constantly you have to dry until it obtain constant weight. So the second example is grain size distribution for sediment and soil sample. So this will able to determine the amount of sand, silt, and even clay in a sample. Okay, because these three type of soil sample have different in terms of its grain size. So the grain size boundary for the sand and silt is 1/16 millimeter, and then for silt and clay, the boundary size is 1/256 millimeter. So based on this, we can differentiate the three types of soil due to their different in terms of their size. This is quantitative calculation involving particulate gravimetry. Okay, so we'll have 200 milliliter of water sample, and this water sample is filtered, okay, through a pre-weigh glass fiber filter. So means this glass fiber filter weigh first before the filtration process, and then this glass fiber filter subjected to drying until it obtain constant weight at 105 degrees Celsius. The drying is conducted at 105 degrees Celsius. Okay, the weighing process is conducted after it cools down. Okay, you have to let it cool down first, then you weigh. So the filter was found to have increased in mass by 48.2 milligram. So determine the total suspended solid for the sample in ppm. So if you refer back to your LU2 lecture notes, ppm means milligram of analyte per liter of solution. So by the definition, it means milligram per liter. So therefore, you are given the information here. The filtering medium or the glass fiber filter has increased in mass by 48.2 milligram. So that actually represent the mass of the total suspended solid. okay, here. And then the initial sample water, the volume is 200 mil, so you convert it to liter, divide by 1000, you get 0.2 liter. So 48.2 divided by 0.2 divide with 0.2 liter, you get 241 ppm. So this is the total suspended solid for the sample. Okay, the last part is the exercise, okay, involving particulate gravimetry. Concentration of airborne particulate in industrial workplace was determined by pulling the air through a single stage air sampler equipped with a glass fiber filter. The air was sampled for 20 minutes at a rate of 75 cubic meter per hour. So at the end of sampling period, the glass fiber filter was found to have increased in mass by 345.2 milligram. So what is the concentration of particulate in the air sample in milligram per liter? Again, it is asking for unit of milligram per liter. Okay, so we have the mass here. Okay, how about this volume here? Okay, look at the information in this sentence here. The air was sampled for 20 minutes at a rate of 75 cubic per hour. So means it was only sampled for 20 minutes. So in 1 hour, you should get 75 cubic meter. But in 20 minutes, okay, so if 1 hour, you have 75 cubic meter. Okay, in 20 minutes, how much air? Okay, so this is how you solve it. Okay, so the air was sampled for 20 minutes only, so therefore only 25 cubic meter of air will be sampled in that 20 minutes. So we have to convert this cubic meter to liter first, because the final answer needs us to solve it in milligram per liter. So 1 cubic meter, okay, the unit of conversion is 1 cubic meter equivalent to 1000 liter. So therefore 25 cubic meter equivalent to 25,000 liter. So you just substitute this into the formula, you get the answer, okay, in milligram per liter for the concentration of particulate in the air sample. So last part is the second approach, which is extraction. So it can also be used for analyte of the gas phase, okay, solute and poorly filterable solid. Okay, and most commonly it is used for liquid sample. So it will need the usage of suitable solvent for the extraction process. So after extraction, the solvent can be evaporated and the mass of the extracted analyte can be determined. So the analyte can be determined indirectly by measuring the change in the sample mass after extracting the analyte. Okay, for example, you have a water sample here, which is believed to have pesticide. Okay, so how you going to quantitatively determine the pesticide, because the pesticide dissolve in the water? Okay, so therefore one way of doing this is by extraction. Okay, so normally we use this kind of a glass apparatus for extraction. Okay, separatory funnel. Okay, so there's a stopcock here. Okay, this one can be closed, like you close a volumetric flask. Okay, this one can be drained out, like you drain sample from urine. Okay, so you put the water sample here. Okay, and then followed by addition of appropriate solvent. Okay, and that solvent will be able to extract, okay, the, let's say this is the water sample portion. This water sample portion will have the pesticide inside. This is the solvent, so the pesticide can, like, okay, can be extracted into the solvent phase, and then you can drain out the water sample, leaving behind the solvent phase. And this one you can evaporate it off, okay, leaving behind the pesticide. Okay, so that's one way, and you will learn extraction process in more detail in the last learning unit, which is LU6. So that concludes learning unit 3.